Hello everyone. In this lesson, we will discuss the principle of similar polarity and the solvation principle. Learning objectives. First, master the principle of similar polarity. Second, master the solvation principle, based on theoretical analysis and practical experience. The solvent for dissolving polymers can be selected according to the following three principles. First, the principle of similar polarity. Second, the general acid-base interaction principle, also known as the solvation principle. Third, the similar solubility parameter principle. Let's first look at the rule like dissolves like. For small molecules, solutes with high polarity dissolve in highly polar solvents, and solutes with low polarity dissolve in low polarity solvents. The closer the polarity of the solute and solvent, the easier they mix. Like dissolves like. This principle also applies to polymers to some extent. For example, natural rubber, nonpolar, is soluble in gasoline, benzene, hexane, and petroleum ether. Polystyrene, PS, is soluble in toluene, chloroform, aniline, and benzene. Polymethyl methacrylate, PMMA, is soluble in polar acetone. Polyvinyl alcohol, PVA, is soluble in water. Polyacrylonitrile, PAN, is soluble in DMF and acetonitril. The principle of solvation, also known as the solvation rule, refers to the polarity orientation and hydrogen bonding rule. This rule demonstrates that there is an inherent relationship between the solubility of polymers containing polar groups and solvents. Solvents vary in polarity. Moreover, polarity can have positive and negative dipoles. Two substances with similar solubility parameters are more likely to be miscible if their opposite polarities attract. The relative proportions occupied by molecules of different sizes lead to the solvation principle. If a polymer chain, main chain, or side groups contains certain polar groups, the polymer can be classified by the nature of these groups, as shown in the table. Category 1, weak electrophilic polymers, including polyolefins and chlorinated polymers, such as polyvinyl chloride, PVC. Category 2, electron-donating polymers, including polyethers, polyesters, and polyamides. Category 3, strong electrophilic and hydrogen-bonding polymers, including polyvinyl alcohol, PVA, polyacrylonitrile, PAN, and polymers containing carboxyl or sulfonic groups. Solvation rules. First, when the polymer acts as a solute and comes into contact with a solvent having a similar solubility parameter, electrophilic solvents of category 1 and 3 can interact with electron-donating polymers of category 2 through solvation, facilitating dissolution. If hydrogen bonds can form between the solvent and polymer groups, this also promotes dissolution. Second, electron-donating solvents of category 2 can interact with electrophilic polymers of category 1 and 3 through solvation, also promoting dissolution. Third, when electrophilicity is the same, that is, both the solvent and polymer are electrophilic or both are electron-donating, solvation cannot occur, and mutual dissolution is unfavorable. In other words, even if the solubility parameters are similar, Category 1 polar solvents hardly dissolve Category 1 polar polymers, and Category 2 solvents hardly dissolve Category 2 polymers. In summary, Rule 1 is qualitative, while Rule 2 is semi-quantitative. However, using solubility parameter values to determine the solubility of polymers is applicable only to nonpolar molecular mixtures with no heat exchange or slight endothermic behavior. It is not applicable to systems with strong molecular polarity, hydrogen bonding, or exothermic mixing. Therefore, Rule 3 serves as a supplement to Rule 2. Category 1 includes nonpolar hydrocarbon solvents and halogenated alkanes, which are weakly electrophilic solvents. N-hexane 14.3, N-octane 16.0, cyclohexane 16.8, carbon tetrachloride 17.6, toluene 18.2, benzene 18.8, chloroform 19.8, tetralin 19.4, dichloromethane 19.8, chlorobenzene 19.812, dichloroethane 20.0, carbon disulfide 20.5. Category 2 includes ethers, aldehydes, ketones, esters, amides, and amines, electron-donating solvents. For example, diethyl ether 15.1, ethyl acetate 18.4, tetrahydrofuran THF 18.6, butanone MEK 19.0, acetaldehyde 20.0, cyclohexanone 20.3, acetone 20.5, hexachloroethane 20.5, pyridine 22.3, dimethylformamide DMF 24.6, tetramethylene sulfone sulfolane 27.4, water 47.9. Category 3 includes alcohols, phenols, nitro compounds, sulfonic acids, and carboxylic acids, strongly electrophilic or strong hydrogen bonding solvents. When two groups have opposite electrical properties, the closer their polarity strength, the stronger their mutual interaction, and the better their solubility. For example, nitrocellulose contains electrophilic nitro groups, so it can dissolve in solvents with compatible polar groups such as acetone and butanone. The delta value of polyvinyl chloride (PVC) is 19.4. This is close to the delta value of chloroform 19.0 and cyclohexanone 20.2. However, PVC is soluble in cyclohexanone but insoluble in chloroform. The reason is that polyvinyl chloride is an electrophilic substance, while cyclohexanone is nucleophilic. They can form hydrogen bond-like interactions. However, both chloroform and PVC are electrophilic, so hydrogen bonds cannot form, and they are therefore immiscible. In practice, solvent selection is quite complex. In addition to the above principles, factors such as solvent volatility, toxicity, and the intended use of the solution must also be considered, as well as the solvent's impact on product performance and on the environment. Chapter Summary. 1. Like dissolves like, a qualitative principle. 2. The solvation principle. Nucleophilic groups can interact with electrophilic groups.